Hi, this video is about more examples in R. The video has like two parts. The first part is just with some examples that are related to statistics and also the way to do regression in using artificial data. And then the second part will be a more elaborate example using real data and looking in more detail at what you have when you do regression. So for the first part, I'm just opening an empty script, and the things about the second part you'll have in Atenea, the script and the data, and for this I'm just improvising, so I could save the script, but it's very simple. I think you can do without having the script. Also, you see the script in the videos. I think that this is enough. And so, comment. Some statistics. I'm assuming that you know about statistics, and maybe you haven't seen still regression in detail, but the question is, now we are just learning to use the program, and later in the course we'll see an example with regression, more in the philosophy of machine learning. So it would be then when I will explain better what happens in regression. And so the first thing is that you need some random statistical data. The easy way to do this is to have a sample using the random generation functions. And the thing is, for every kind of variable you have a name, like for the normal, binomial, exponential, and so on. And then you have one first letter that tells you what kind of thing you are doing with the variable. So for example, for the norm variable, which is the name of the normal or Gaussian variable, for doing random generation, use R. And you have seen this before, so this is not new. And here you need the number of values that you want to generate, and then the parameters for the variable, and usually there is a default choice. So if you say nothing, in that case is 0, 1, mean 0 mean and 1 deviation. And let's check. So now you have, for example, those 10 numbers, which are random sampling. And if you want different parameters, like mean 5, and and deviation 2. So now you have numbers that go around 5, which is the mean. So you can choose the parameters that you want. And let's change this number to have something a bit more statistical, like 100 values. Okay, so this is the sample. So basic things when you have one vector that has some statistical mean, well, in fact for any vectors you could use things like this. One is the length of the vector. So this is the number of values in the vector. In that case is 100, which is what we ask. And what more can you do? You can sum all the elements. So in the vector, Control R. So since you have 100 values and the mean is 5, you expect something close to 500, and in that case is 487. And you can ask for the maximum and minimum value. The minimum element in X is minus 0.87, and the maximum element is 9.6. And then you can compute the sample mean of X. In that case, this should be close to the mean of the variable. So as you know, the 5 and 2 here are the parameters that you have in the density, and when you take a sample, then you can estimate those parameters by doing, for example, like here, the sample mean. So this is 487, which is close to the mean. And of course the mean is just the sum, Control C, divide by the length. So that's, as you see, the same number. Other numbers that you have here are the standard deviation, which is computed from the sample, and in that case is very close to 2. The real value is 2, and the sample value is 1.997. That case very close to 2, but this could be also by chance. And you can also have the variance is almost 4, and if you remember, the variance or the standard deviation is the root of the variance. So the square of the deviation is the variance. As you can see here, it's the same number. And if you know a bit about the sample values, you have two versions of the deviation. One is the biased version, and the other one is the unbiased version. And this one is the unbiased version, which means that when you divide by the length minus 1. Divide by n minus 1. And so SD and bar give you the unbiased versions. If you want the biased versions where you divide by n, then you need to scale the value. I think maybe you can test this by doing so what's the standard deviation? You do the sum of x minus the mean of x. The mean of x is like a constant, so you are subtracting this constant to all elements, and then you do the square, and that means the square for every element, and then you do the sum. And finally, you should divide by the length of x. And this is the variance, okay? This is the variance, and if you want the deviation, you should do the square root of this. Control R, oops. Yes, bro. This. So now you have here this number, 1.987, which as you see is different from the one you have here. And the unbiased version is dividing by n minus 1, which is a small correction, but in that case, as you see, now this number is the same than this. Okay, so we have this, and what else? You can use the syntax to extract pairs of the vector or get some information. For example, if you want to see how many elements are, since the maximum was 9, so how many elements are larger than 8. If I do this is a Boolean operation, so this gives me this thing. If I want to count how many true elements you have, you can do the sum, because this will force the Boolean to become ones and zeros. And so you can see that you have 3 values larger than 8. And if you want to see the values, you can take x so now you see which numbers are those larger than 8. And also related to this manipulation of the Boolean vectors, there are 2 functions. Is any element larger than 8? And it says true. So this takes the vector and sees if the vector has at least one true element. So if here I put 10, then it's false because no elements in X are larger than 10. And then you have the all. Are all the elements in X less than 8? And this is false. And are all the elements less than 10? Now this is true. So those are things that you can use to get information from Boolean vectors. And going back to the statistical things, to look at the vector, you usually do the histogram, which is this. So this should be like the Gauss bell shape, but well, in that case it's not too close, but 100 maybe is not large enough for this. And in the histogram you have options. You can check by looking at the help for the function. Remember that you can do this help on any function. This will open the browser, and here you have the options. So you can choose the break points, and also you could normalize in some ways and so on. And you can also put color and some graphical options into the histogram. And another thing you can do when you have a sample vector is the summary of x, and you see here the summary gives you a few values, and the values are the minimum value in x. This is the first thing. The last thing is the maximum value in x. You have the mean here. The mean we have computed the mean before. The mean was this number here. So as you see, the summary gives you the mean also, and then you have the thing which is called quartiles. So the quartiles are the points that have at the left 25%. This is the first quartile. 50%. This is the second quartile, and this is also called the median. And then 75%. This is the third quartile. So when you have a sample, essentially what you do is you put the elements in an ordered way, and then you divide in 4 equal parts, and the points at the divisions are the quartiles. And in that case, those are estimations of the quartiles for the Gaussian variable with the parameters we have. So the summary gives you those values. This is like a vector with named elements. So let me check this. Class of this in a variable, and then check sum, and well, this is a table, essentially a table. So it's like a matrix, in that case with only one column and names for the elements. And a few more things related to statistics is, so now you have one kind of variable, which is the normal variable, that has this name, and with the R letter at the start, you had the random generation. What other options do you have? One is when you put a P, then you get the cumulative distribution function. So this gives you the distribution function for the normal variable, and if you remember, this is something that depends on the error function. So it has not an analytical simple form, because it's an integral that you can compute in an easy way, combining basic functions. So in that case, the p-norm, the argument is the value of x, where you evaluate this function. For example, if I try 8, and now I put the same values we had for the mean and deviation. So it's like the first is like the variable would be like x. This is not related to any sample, no. This is just to get a number for this kind of variable, and those are 5 and 2, the parameters in the density. And I don't know. And this is just a number, and this is 0.9, which is close to 1 because we are far at the right of the mean, which is 5. And one thing that we could do is to try to plot this function to see how it behaves. And for this I need the vectors with the x and y coordinates. For the x I use tip because I'm using the x for the sample, so I use t, and I use a sequence, and I will start, since the mean is 5 minus 10 is minus 5, and 5 plus 10 is 15, so I will use this interval, and then the number of values, length, equal, so this is just to have a smooth line. And next I want the y values, which are the function applied to those elements. So what I need is this, Control C, and as this is the cumulative distribution function, how to call this? Well, I will put uppercase F, and then is this applied to t. And finally I should do a plot of t, f, and what else? Maybe the color could be blue. That is that parameters in that kind of parameters are like strings, and for strings you can use the double quote but also the single quote. I mean, you could do also with this one, not mixing them, but any of them will work. And then maybe the line width a bit large. So let's try all this. Notice that I have a window with graphics, and since this is the basic interface, well, now I will kill the plot I had, and let's see if this works. Okay, and so you have here the plot. And I forgot one thing, which is type equal L from line, because I don't want dots, and that's it. Control R. Okay, so this is the plot, and as you know, the distribution functions come from 0 and go to 1, and then is an increasing function which is continuous for continuous variables, like the normal variables. And so this is one thing that you have. If the letter is D, what you get is the density function. This depends if you have a discrete variable. This is the probability function, which could be more useful done, but for a continuous variable, this is the value of the density, which you don't use really usually in computations, but you have the function. And Control R. Now this is a small value, of course, even if you are at the mean, which is the maximum. This is 0.2. And then we could repeat this. The t I have already, and now I copy this, and let me put this up. So now I have the density, so here I need a d of the vector t that I already have, and then I will plot the density, and let's check. Control R. Okay, so this is the Gauss shape, and this is something that you can do for many types of variables, but you should know the names of the variables. For this, remember that, well, besides the books and the online reference you can get, here in the help you have the manuals. An introduction to R is maybe the most basic manual, and it's something that maybe you should have a look at. And so you have many chapters here, and one is probability distributions. And so here you have the names of the variables. So you have the Poisson, normal, student, uniform, well, geometric, Cauchy, binomial. So those are, this is the name of every one of them. So you need this for working with them. And you can do what I did for the normal with any one of those variables just by changing the name in the code. And so let's go back here. And what else? Well, another option you have is so with R you generate values, with P you have the distribution function, cumulative distribution function, with D you have the probability or density function, and finally you have the Q, which is the quantile function, which is very useful for statistics. And so in any book of statistics you have tables for this thing. This is like the inverse of the distribution function. Here you select what probability you want to have at the left of one point, and then you get which is the point. So for example, for the 5-2 variable, what point would have 0.75% of probability at the left? So this should be at the right of 5, and this is 6.34. Notice that this corresponds to the third quartile by definition, and in that case the value you had before came from a sample, so it's like an estimation. But now this is the value for the variable. So this is the number you were estimating before. And so if you want to have 1% probability, you have this value here. So you can choose the area of the tails and see what's the point for the tails. So this is something you use a lot in statistics. So let's go to regression now. In statistics, well, you have many topics. Usually you start with the descriptive statistics, with just looking at the numbers, computing the means and the sample mean, and this, doing some plots with histograms. So we have seen a bit of this. Then you go to estimation of parameters. This is one typical problem, getting estimations of the parameters of a variable using samples of this variable. And then the next chapter is like hypothesis testing hypotheses, usually about the parameters. And then you go to regression. And in regression you have more than one variable. And for this I'm building a two-dimensional variable. X, I'm using the normal. So let's say, how many values? Could be like 50 maybe. Then the parameters. And then I want a y variable. So let's first put just this, and with the variables I can do a plot of the points. So now this is just the dots for every x, y coordinates. So this is a sample, and the x vector has all the values for the x coordinates of the sample points, and the y vector has the y coordinates for the same points. So if you do this plot, you'd see the points. And see what happened in that case. You have this, and well, you see no special pattern here. The center is 5, 5, of course, because of the parameters. And with the deviation, you can make this more white or more concentrated. But the thing is that no special pattern is present here. And this is because this is independent. So if I do the y the same way I did the x, I get just random values with no correlation. You can compute the correlation coefficient, which is called COR. And as you know, this goes from -1 to +1, and when it's close to 1 or -1, it means that you have a strong linear correlation. And if not, then you are close to 0 and there is no correlation. And this is similar to independence, and in fact in that case is equivalent to independence because the variables are normal. For normal variables, correlation equals 0 implies independence. So you know that they are independent in that case, so the correlation should be close to 0. Of course, this is a sample correlation, so it's estimation of the correlation. Control R. So it's minus 0.12. As 50 is not too much, so you are not very close really to the values when you look at the estimations. But I prefer less points so you can see more of the structure of things. And this is the correlation, and then you have the covariance. The covariance is the non-normalized version. So this is not restricted to an interval. In that case, the covariance is this minus 0.57. So you have the mean, standard deviation, variance, covariance, and correlation coefficient. So all the basic parameters for 1 and 2 degrees are easily computed for a sample. And so let's make this a bit more interesting, because if there is no correlation, there is not much that you could do here. So what I do is, when I create the y, I just use the x. So let's say that we have the x, multiply, for example, by 2, and then we add this other thing. So still you have something which is random, but now there should be some relation between variables. So let's try this. Control R. Now the plot. And as you see here, now there is a difference, because the cloud of dots has a shape which is a bit linear. It's a bit linear. So you would say that you have some correlation, linear correlation. And the thing is, for example, in that case, this is a positive correlation. The larger you take the x in mean, the larger becomes the y. And of course this is random, so anything could happen, no? But the weight of the probability is around something that has the line, the shape of a line. And so this brings us to regression. The idea of regression, and this is something which is belongs very much to machine learning, which is that you have some data and then you want to, at the end, maybe to do predictions, no? But predictions that imply that you have a model for the data that you use to make the predictions. So here you expect to have a model, and then when you compute the model, you can predict values. And so the basic technique is which is called linear regression. And the idea of regression is that you have a function that when applied to the x tells you something about the value of y. And then we say that this is estimation of y. And one way to think of this, so this is about regression, is that more in general, your x is estimated, your y is estimated with a function of the x variable. And there are several ways to write this. One, I put uppercase because usually random variables are named in uppercase. One way is to say that the estimator, but I don't know if this, sorry, I can put the hat on the y, no, but the y with a hat, maybe, well, no, sorry, it doesn't work, but then the white estimator, let's put it this way, is equal to a function of x. Or you could write that y is estimated, I use the same value. This is the tilde, which is, let me put it this here, the tilde symbol is the key at the right of the space, which is alt space here, this key, plus the number 4 that you have at the upper row of the keyboard. So when you use those two keys, you get the tilde. Sometimes the keyboards have not this symbol in the keyboard, but I think that this works usually. Depends on the language for the keyboard. And so this is one way to say that the function f on x estimates y. And another form is to put an equal, and of course since y is not a function of x, you have something else. It would be like an epsilon, but I don't know, some error. Okay, so a model is this kind of pattern where you have some fixed function that you can evaluate, and you have to compute in some way, and an error. And of course you choose the functions in a way that the error is as small as you can. So by minimizing this error here, and since this is random, minimizing is what you minimize is the expectation of the error, because now here everything is random, but then you make things small by using the expectation of the square, essentially, because the expectation could be 0 for the signs of things, but if you put in a square, then this gives you a measure, a magnitude of the variable. So this is the general idea, and then you have linear models. So this f of x is a model, but the ones which are easy to compute, and in some cases are enough for doing this are the linear models. A general form for a linear model, the essential idea is that you combine random variables. This is the linearity. So for example, is that you estimate y. See, if you only have x, then this could be a1 multiplied by one function on x plus a2 multiplied another function of x plus up to I don't know, fr of x, uppercase, and then these are. So this is the general form for the linear model. And one special case is simply estimating by one constant multiply x. Oops, this is a plus and another constant. So this is the basic linear model. There's always this problem that we use the linear word with two senses. One sense is the fact that this is a straight line in the plane, but the other sense, which is the important one, is that your estimation depends on the constants in a linear way. And here it's a linear way because there is something multiplied by a plus something multiplied by b. This other something is the number 1 in that case. So when you combine random variables, and the constant is a particular case of a random variable, then you have a linear estimator. And what I mean is this last thing is linear, but this one is also linear. So, well, if I put an equal, then I have plus the error and so on. And it could be this a multiply x squared plus b multiply x plus c. And this is linear still in the sense of regression, because this is a multiplied by something plus b multiplied by something plus c multiplied by something, which is 1 in that case. But notice that now this is not a line, a straight line as before, because this is a parabola. So in that sense, you wouldn't call this linear because it's not a straight line, but in terms of estimation, this is still linear, and you compute this the same way you compute this. And you could also use more variables. The names for this is, there is one variable that you want to predict, which in that case I'm calling E. This is called something like response, I think. And the X variables that you use to do the prediction are called predictors in statistics, but also in machine learning in general. Features or other names. So the idea is that you have data that corresponds to samples, and then you want to build a model that has some specific form. And in that case, if the model is this kind of function, here, so I forgot the error, then you have linear regression. And this is very easy to compute in R. Let's see the way. And it goes this way. First you need a name to to keep the output of the regression, I will call this rec. And then the function that performs the computations is lm, that comes from linear model. So this is the basic linear model. And then the input is the formula, especially. You can put other arguments, but the main argument is the formula. The formula tells you what you are doing here. Like, do I want a parabola or a straight line, or combining two different variables, whatever. And for this you have a syntax for the formulas that have many variants. And in the, let me see if I can see this, okay. And so here I think you'll have statistical models. You have here an explanation, and here you have the different formulas. So there are lots of possibilities, but the one we'll use is the first one. And by default, when you write something like y, this is the thing you are trying to predict, the tilde, and then the variables that you use and the form of the function. And if I put just this, it means that you have ax plus b. So you have two parameters. And a is called the slope, because it's the slope of the straight line, and b is called the intercept, because when x is 0, this is where the line cuts the y-axis. So intercept and sloped. And in that case, this is enough to get the values. And I will explain this later in the course when we use regression as just one algorithm for machine learning. But you should know a bit about this. What you choose the line in a way that makes the error the smallest possible, and for this what you minimize is the squares of the sum of the squares of the distance. So this is a minimum squares kind of computation. And for this you have some formulas that are easy to compute. At the end you have like a linear system with as many variables as parameters you have. So it's something which is not difficult to compute. And here you have, in an automatic way, this. So I run this. So now I have my rec. And let's see what we can do now with the rec. And the first thing is just call the name to see what information this gives to us. And this is not much, it's just call. That means what you ask to the linear model, so it remembers you which formula you have. And then you have just the coefficients, and see that one is the intercept, this is the b constant, and the other is named with the variable that multiplies it. So in that case the model is 1.75 multiplied by x plus 6. If you want more information, you can do the summary. So the summary can be used for many structures. So rec is some kind of list because it holds different pieces of information. But this is a class in itself. So now the summary gives me more information. And let's see what we have here. One is the formula I used to call this model. So this is the same than before. Then you have the one thing which is called the residuals. The residuals are like the errors. Once I have the line, for every point I have the vertical distance to the line. And those numbers are called the residuals. they can be positive or negative because they could be above the line or in the other side of the line. And so you have some statistics for this set of values. So this is a vector that has, in that case, 50 values, the 50 vertical distances to the line. And here you have the minimum and maximum, so this is a measure of the maximum error you could have. And then you have the quantiles and the median. And by construction, it happens that the mean is 0. That the mean is 0. So in that case, the median. So this is the reason why you don't get the mean here, because the mean, one of the equations tells you that the mean of the residuals, the sample mean in this sense, is 0. So they don't give this information here because it's always 0. And of course the median is close to the mean if you have symmetry, like in the normal variable. That should be the case here, but in that case, this is not exactly 0. And the next piece are the coefficients. So you have two rows, one for the intercept, another in that case for the variable you have, and this is the coefficients. So which it says estimate. Why estimate? Well, I will explain this later. But the thing is that you have theoretical, let's say, values for this that come from the density, and now this is like estimating those values. And then you get the statistical information that I will not comment now. But this is some kind of test of the hypothesis that those values could be 0. So the thing is, if one variable is irrelevant, then it's 0. So you are testing this. And here you have a significance value. So the more asterisks you have, the more sure you are that they are not 0. And this is clear because this is 6, and this is 1.7. So you are very far from 0. And finally, you have some measures of the error, and one is about the quadratic error that you have here, but the number that you look is the R-square value. The R-square value is some kind of correlation value, but since this R-square goes from 0 to 1. 0 for a very bad fitting, and 1 for a perfect fitting. So if the line passes through all the points, then you get 1. So what you expect is to be close to 1. And is this possible? But not, because what happens is that some part of the dispersion may be explained by your model, but some part is just noise. So still you have something random that it's impossible to predict. So when you build the model, there is a limit to what you can do really with the model. And of course you could fit very well any kind of data you had, but then when you got new points, your model wouldn't be useful. I will explain this later, but which is called the problem of overfitting. So of course you build the model in some data, and the thing is that you want the model not just for this data, but for predicting new instances. So in that case, you could fit very well what you have here, but then with new points, it wouldn't be useful. And in fact, you could think, okay, why not to try now second degree or other things? And if you know something about random variables, the normal variables have the property that the best possible regression you can do is the linear with the straight line. This is a special property of the normal variables. So if you do here a parabola, of course you will improve in the R² value, but it's an improvement which is artificial. It's because you are trying to fit very well the points you have. So it wouldn't be a better model. And in fact, you should see that the coefficient for the square should be close to 0. So I think it will fail the test here. So that the number to look is this one here. And in that case, this is a 0.76, which is not very high, but maybe given the parameters you have here, is the most you can do. So in the future, maybe I will explain more details about what you have here, but no, I just want to focus in the R² value and the coefficients. And if you need the coefficients, notice that this works as a list, so you can do things like this. Rec $, which is the thing you use to access, and then coefficients. And this is a vector, Control R, as you see here, a vector with the coefficients. And then you can save this in a vector and use the vector to do things with those coefficients. We'll use this later. And the next thing is, okay, let's plot the line. And there is a very easy way to do this for the straight line, which is, now I have a plot, let's say active, because this window is open, and I just want to add something here without closing the window. So what I do is use the AB line, which is used for drawing straight lines only. But the thing is, I can pass the rec, and then the function will know what to do. And call equal red, oops, what I did here, sorry, equal red, for example, line width equal 2, and so now you have here the plot. As you can see, the line is a good fitting. In that case, it follows the shape of the cloud. So this is an example of linear regression. The name of regression comes from the fact that maybe you have points that should be in the line, but for experimental reasons or for errors that you have in the measures are not in the line. So in that case, what happens is that you want the points to go back to each place, to regress to the right position. So this is one possible context for this, but in our example, this is just really random. You have something which is random, and that's all. But if the randomness came from some experimental errors, then this could make sense as how to get the dependence that you want from experimental data. And that's essentially the thing. And if you want to play with this, you can do the same I did, which is getting, let's say, where I have this x and y, okay, like here, changing parameters or the type of variables or things like this. You can work with more variables, but then you can't do the plot, because for the plot, if you have two predictors, things happen in higher dimensional space, and well, it's more difficult to do. You can do still maybe in 3 dimensions, but it's not, things are not so clear as we have here. And the other thing is that you can use real statistical data. And you can, we'll see this in the next example, but one thing is that you have statistical data in the program, in a package, and if you just ask this, you'll see what you have. So okay, here opens a window. I don't know how this works in RStudio. And you have the names of the data and a very short explanation. And this is something that you can load in an easy way. I will show you now. And then you can do statistical computations. I haven't used really too much of this, but the one I would like to use is the cars. This one, cars. So it's just very simple, speed and stopping distance. So the car goes with some speed and then you stop, and what's the distance you run before the car stops running. And for this, what you do is this. So let's check what variables do you have now. I have defined several things, as you see. So this is what I have. And now if I want to work with the cars variable, what I do is data, and then I call cars. And if I repeat this, you can see that now you have cars here. And let's look at the object that we have here, cars class, is a data frame. So this is an important structure because it's the one we'll use always to work with data. And a data frame is like a matrix, but it's like a table where the columns are the vectors with the variables that you have. So for every variable, you have one column, and then you have one name for the variable. And this is a special type of list. So it has some properties which are common to the list object. One way to look at what you have in that case is use the str, which means structure. You can use this for any object, for example, for x. So in that case, since it's a vector, it does nothing else. It's numeric from 1 to 50 elements, and then it shows you a few of the first elements. And if I do this with the cars structure, it says is a data frame, and now it tells you it has 50 observations. That means the number of rows. So we call these the instances that you have. And then the number of columns is the number of variables, 2 variables. And it tells you one variable is speed and the other is distance. Those are the names of the variables, which are numerical, and then you have a few values for them. So if I want to do a plot, I could call the data frame, and you see all the values here. Always you have a number, which is a numbering of the rows, and then the first column is speed and the second is distance. And you can access information but using the brackets. So the first row is this one. And if I want the first 5 rows, it would be like this. Sometimes you call head without telling how many rows do you want to see. Head of cars to see how it starts, and in that case it plots six rows. So head is generic for any data frame. So the data frame has these properties. Number of rows, which are instances. The number of rows is this 50 is like the end of the statistics. And here you have the number of variables. So if you have one response, that would be one column. And if you have predictors, they would be columns also here. And you usually have names for the variables, even if you can do by just using numbers, like here 1, or let's say 2. So I have only values from the second column, as you see, 2, 10, 4, and so on. But I think I could put also the name here, like, I don't know, dist, and this is the same. And now that you have this data frame, you can do a plot of cars dollar. So dollar is the thing to access. Let's put first the speed. This is the logical way, and then see how distance depends. So dollar dist. And now you get a new plot here, and those are the dots that you have. And there is a positive correlation, of course, so the faster you go, the more distance you need to stop. And so this is some statistical data. And you could do the regression in the same way as before, doing rec cars, for example, linear model of. Now what you write is like this. You want to predict dist using speed. And why not the dollar and the name is because you can then put data equal to the name of the data frame. This is very typical. So you pass here the name of the data frame, and now you refer to the variables without all the syntax. So this is the regression, and now the AB line for this regression, and call equal red, and line width equal to. And so this is the regression now. But now this is just some statistical data, so it doesn't need to be normal. And so maybe this is not the best regression that you could have. So here you could try other kind of regressions. But since in the next example we'll do this, no, I'm not trying to improve on this. In that case, the summary of rec cars has an R square which is not 2 watt, 0.65, so you can see here. So maybe a parabola would be better. Maybe a parabola could improve on this. But I really don't know because I haven't tried. So, but well, this is the thing. And then when you have the model, of course, you can try to predict what if the speed is 30, then you get a prediction. In statistics, you always use the hypothesis that your data is normal. And then you can compute some errors and give some probabilities to what's happening and this. But if the hypothesis is not true, then it's difficult to say something about the kind of errors that you have when you predict. In regression is not a good thing to go outside the interval where you build the model. What usually happens is that the errors increase as you get far from the center. So there is a danger in this kind of prediction. And so that's it for the first part, and then I will close the program and open again with the example that I will work that has more sense than the artificial examples here. Well, now I have opened a new session, and for the second part you need the data that we'll use, and this you have in Atenea, the course. And remember that you have the data for the examples at the end, but in that case I have this in the examples part, so this is now visible, and the data we'll use is this file here. And this is just a text file that you can download, so, and then the name is lusage.txt, and I have it already, so I'm not. And if you click here, you will see the file because it's just text. And this is a data frame with 4 columns. And this data is about electricity use in function of temperature mainly. So the information you have here is many instances, and for every one of them you have the month of the year, so 1 to 12 here, January and so on. You have the year, so in fact you have information for not just 1 year but several years. Then this is the quantity of electricity you used, or the person corresponding to this instance used in that case. So this is kilowatts hour. And finally you have the temperature. And this is Fahrenheit, so maybe it's difficult to interpret, but you could transform maybe to Celsius, but that's the information you have. So the idea is how this electricity use depends on temperature and maybe also the month. So you have essentially 3 variables which are related. And you have also the year that you can use to have more statistics because you have more sample for the same month and different year. So that's the data you have. And so in that case, the data is in a file that you should read from the program. So the first part is you should save this in a place where you can then go to get the data. Let's go back here. And so we are here, and the thing is, once you have your data in some place, the better thing is to switch the directory to the place where you have the data. So you don't have to worry about the path, the full path for data. So you go to File and change there, and then you can choose the place where you have things. But I did already, so I want to know. And for this, you'll have the script in Atenea with the outputs and the plots. So by now, I'm just recreating it from zero, but it's just like copying what I have written. So I do this from a blank script. So if you want to check about directories, remember that get working directory tells you where you are, besides the menus and such. Also, you could do a dir to see what files you have here. So let me see, for example, lush.txt. So I have the file here. So Control L to clean this. And so this is a table that should be in a data frame. And the way to do this is, okay, let's give a name to the data frame. So df from data frame, and maybe el from electricity. And so now you want to read from a file, and in that case you use read table. And now you have to give here the path to the file as a string. And since my current directory is the one that holds the data, lush, just the name of the file, text. And another thing is I will add header equal true, because my file has a header. If not, the first row could be interpreted as names for the other variables, and so it should be clear what you have. So I have a header, and then I tell this to this. So this will read data, and it should be this way. So it's done, and no answer here. If something is not well, you'll have an error. Maybe it can't file the file or something like this. So then you can check the directories and try again. And so what's the thing here? So let's see. The class of this object is a data frame. As I told you before, is a kind of list. And let's do the structure of this. So this tells you that you have a data frame, 55 observations, that means the number of rows, the instances, of 4 variables, that means the number of columns, number of variables you have, and then here you have the names of the variables, so what you have in the header, month, year, and so on. And then it tells you that some are integer and other are numeric, that means like double. And then you have a few values, a few of the first values. So you have this structure, and not that we need this no, but other things that you can get is the dimension of this. Of course, this is a vector with the two values, number of rows, number of columns, like in a matrix. And if you want only one of them, and call thing is, and call is the number of columns, should be 4. And then let me put some space here, and row is the number of rows, so this is the end of the statistics, let's say. So 55. And what else? Names are the names of the variables, so this is like a vector with all the names. This is something you can change if you want. Names, for example, if you don't like the uppercase here, you could change this thing. Names of Dave. So those are the 4 names. So this is a vector with 4 strings. And so this is a bit of information. What else could you do? One thing is the summary. The summary goes to the columns and does a summary for every column. Control R. So you have for the month, year, and so on, as we saw before, minimum, maximum, the mean, median, first quartile, second quartile, which is the median, and third quartile. So you have this statistical information. Of course, you could do histograms for the different values. And if you want the individual vectors for the columns, you access them with the dollar, for example, the temperatures, and this will be the 55 values for the temperature. So now if I want a histogram for this, could do Control R, and I have this histogram, and so that's it. I could work with the vectors in the columns. And you can access parts of the data frame using the bracket notation, and you can use numbers 1 to 4, all, or only the third. So now this becomes a vector, not a column, but notice that this is this column here, and you could use names also. This is called KWH, and it's the same. Okay, so you can refer by name. So you have all those options: the dollar notation, the selection by using the brackets, and so you could get apart. And more complex way to choose a part is using which is called the subset, where you could ask for, in this data frame, first you can filter columns. So this is called select, and this is what columns do you want to keep. So let's say I want let's say temp first, and then KWH. And also I could have an option subset that tells what property should be the the data I'm taking, and this is like a Boolean condition. So let's say that I want the month to be, so this is equal because it's Boolean comparison. Let's say I only want to see the January data, so that's it. So for January I have those numbers here. Of course, if I switch to 7 here, it's like July. Now I have this. Notice that, like, how the temperatures are larger than before. So if I can do this now, is because I have several years. So, well, I could do it in any case, but I mean that fixing the month gives me still several values, because the same month in different years is what I have in the table. So you can select pairs or do things like this. And what else? One thing that I will do now, but it's not a good thing to do in general, is the thing is that if I want to use one of the columns, I have to use this syntax here with the dollar. If I want to use just the name of the variables, what could I do? One would be like create vectors, like something like this, for example, not temp equal to this, and then I create a vector that holds this vector. But there is an easy way to do the same, which is attach when you attach a data frame, the variables with its names become like vectors that you can use. So I do this, attach, and now if I haven't created this vector, but from 1 to 5, now this vector exists. So I don't need this kind of syntax. Still, I think it's better to keep the integrity of the database and always refer to it, but in that case I will do things with the different variables, and I think it's better to have this syntax more simplified. And now that I have this, let's try a plot on a data frame, so it's not clear what will happen now. The FL, and let's see what we get here. It did something, and as you can see, what it does is the plots for all pair of variables. So in the diagonal, of course, you have nothing because it's one variable against the same variable. That would be some kind of straight line. And then you have all pairs. And you also have, for example, x versus y, and then at the other side y versus x. So you have all the pairs. But of course, the ones above the diagonal are like the same that you have under the diagonal, but reversing changing the variables. And some of the plots are not interesting here because the year doesn't play really too much. Things. So one thing you can do for example, in the plots is to filter here and just say that I don't want the second column, which is the year, so put a -2. So this is the whole data frame, but omitting the second column. And if I plot this, Control R, I get only the plots with the interesting variables, not the year here. You still see the year because you have, as you see, several points always at the same x value or y value, depending on how you put things. So this is a easy way to look at the variables you have. You can also do histograms and other things, but it's always a good thing to have a look at what you have. And so let's focus first on, we'll do things with pair of variables. And the first pair is temp versus, or at reverse, temp and energy. And so the dependence is like energy should depend on the temperature. This is the way that we would look at things. So the plot should be like this. Temp. So this is the first thing we want to study. And as you can see, you have a correlation. In fact, this is very similar to the examples that we did before with normal variables. But notice that now the correlation is negative. That means that when you increase temperature, then you lower the energy consumption. So the thing is, this energy consumption is because of the low temperatures, and you need to heat the house and all of this. So in that case, the correlation is negative. We can check curve of temp and this. So this is the correlation coefficient. You can see minus, negative, and close to 1.88. So you have a good correlation, and you could do a good linear regression. And so now the syntax for this is as before. And it's again, I will call this rec tk to know what variables I'm here, and this is a linear model where I want to predict k w h tilde algr4, remember, and now I'm using temperature as predictor, temp. Control R. Let's do the summary. Rec tk. Okay, this is the summary. Here you see the coefficients. The intercept 116, and the coefficient of the temperature is minus 1.3. This minus tells you that the straight line has this negative slope. And then for the R squared, this is 0.78, so close to 0.8, which is not bad. And for the plot, a B line of rec tk equal red, line width equal to, this is just cosmetic, but, and then control R, this will add the line, and that's it. So this is the regression in that case. And okay, that's an example, and now let's look at another thing, which is month and temperature. So let's do like the same, but with two different variables. And so it's like copying this and this. Control C, Control V, and now I will change this. So here I want month, and then how temperature depends on the month. And one thing about the temperatures is those are Fahrenheit values. If you want the Celsius values, you can change, but I won't use this transformation, but you could transform it also in the data frame. And this is something that you do when you scale your variables or normalize the values. This is important in machine learning. And for the temperature, what you should do is to subtract 32, and then you multiply 5/9. You check before, and so those are the Celsius values. So this will make more sense. You are not from America, and I would put around, maybe with one digit. Okay, so those are the Celsius temperatures. So that's it. I'm not sure about the meaning of the temperature. I think it could be the mean, the maximum, the minimum. I don't know. I'm not sure about this. And okay, so anyway, let's do the plot, month and temp. So this is the plot now. As you see, this is very different from what we have had before. Of course, month is not a random thing, so this is why you have here several points at the same place, because the month is 1 to 12, and in different years you repeat the month. You don't repeat the exact values, maybe for temperature or energy, but in that case you have this structure. So this is how many years you have in your samples for the same month. And of course month goes from 1 to 12. And then you have the temperatures for this. So of course this is not linear in the sense of have a fitting with a straight line. And when you compute the correlation, let me see if I can Control C. In core, now I put those variables. You can see that this is not a high correlation. It's 0.25. So this is more close to independence than, but in a linear sense, of course. Notice that your data could be very correlated if it fits very well in a line, but if the line is not a straight line, the correlation coefficient can't measure this, so it could be 0, even if you have a strong correlation which is not linear in that sense. So in that case, you have a structure, you can see the shape, but this coefficient can't capture it. So what happens now is that if you repeat what we did before, you put here month, let me think, that's month and temp, empty. I will put 1 because I will try other. And then here you predict temp for a given month. And then in the summary, I should try empty one, and in the line empty one. So first compute the correlation, then do the summary. So this is the summary from coefficients, but notice that the R square value, which is here, is almost 0. So this is a very bad fitting. And of course, it's bad because when you do the plot, it's very evident that this line, the red line, has not much to do with the data. So in that case, you need another kind of estimation, which is still linear but doesn't correspond to a straight line. And the first thing that you maybe could try here is a parabola, because this has some curvature, and so the parabola is an extension of the line and it's not a very complex model. And the thing always is that you could use very complex models in any case, but you want the maximum simplicity. So we start with a line, and in that case the line has no sense, so you want to improve, but you want to keep the model as simple as possible. So the thing is, okay, let's put another term like an square, x square kind of variable, and see how this can improve the situation. So what I need to do is like to repeat this with another estimation. And so let's say that you want to do the parabola. So the thing is, I will call this 2 because it will be a different regression, and then the plot will be very different because the AB line is only for straight lines. And here there are 2 ways to do this. Let me do the first one. I want to use month, and I want to use month square. So this is one way to put things, but this would give you errors, and you need to put this y here, I of this. So this is something that belongs to the syntax, but that means that you have the intercept, but now you have those 2 variables, and then you are combining a plus b month plus c month square. And let's do first it this way, Control R, and the summary, and let's look at the R square. Notice how now this is a 0.87, so it's almost 0.9, which is a high correlation. So it has been a strong change, because before was like almost 0, and now with the parabola is a high value. And the other syntax, it could be better if you want to use higher degree polynomial, maybe, is this one. You have to write here polynom, and then I think it's the variable month, then the degree, which is 2, and then row, which is an argument, should be true. And the only thing strange is this row equal true. This is because if you don't put this, it uses another kind of polynomials, which are like orthogonal polynomials. So if you want the typical 1x, x squared, and so on, you need to say this row equal true. And so this is like the same. Control R. As you can see here, you get the same coefficients than before. You can compare, and it's all the same. Okay, so it's no difference in what you get. One difference is that there is something not right here. Let me think one moment. I don't know what I did. I did Control R. Okay, sorry. The thing is, I didn't run the line. So yes, this is poly. Sorry. Okay, now it ran this. Okay, so that's it. So you have the same numbers than before. The only difference is in the coefficients. Before you had intercept, month, and month square, and now you have poly 1, poly 2, which are the degrees. And the good thing about this is that you could put another degree here and have another very easy modification for getting higher degrees in the polynomial. But now you have only 3 coefficients, which is a good thing. And so this is the regression. And okay, the fit is good because the coefficient is close to 1, and you want to plot this parabola, and I have to start again here. Let me see, Control R. So now we have the plot for this. And now this is not a B line because this is not a straight line. And the way to do this is to first I extract the coefficients, mt2, because I want to refer to. And to do this, you take the regression, reg mt2, $, and then coefficients. So this is a vector that holds the coefficients, mt2, and maybe this way doesn't look nice here. Maybe as matrix we'll put this in a column or something like this, or you see. Okay, this is better. So you have in a column the coefficients with the names of the coefficients. And now what I do is, okay, I need to do the plot, the x coordinate and the y coordinate. The x coordinate I will in this way, t. Well, I don't need this for the month. I will use also the 0 to get some movement outside the interval. 0 to 12, for example. And after this, so let's say call time month, time for the month. And now I want to build the line mt2, and I just do the parabola computation over the tm variable. So I have the coefficient mt2, the first one, which is the intercept, as you can see here, plus co mt2 second multiplied by tm, plus, so finally the Control C, Control V, so this would be the third coefficient, and power 2. So this builds the parabola line. And so what I should do is add this line that you do with lines, and then in lines you need the x coordinates, tm, the y coordinates, the line I have here, mt2, and for the other, the color, the line width. I think that maybe I need the type or not, because it's lines, you don't need the type equal L, so you have to run all of this, I think, Control R, and the coefficients I had before. Okay, so you see here the parabola. And so that's the fitting that we have now. And of course the parabola can follow the shape and do a good fitting with 0.87 r square. And well, one final thing is, could you improve on this parabola? Well, one thing is go to a higher degree. In general, this is not a good idea unless you are sure that your data is has a polynomial dependence. And in that case, one thing that you are not using, and in fact goes against the use of polynomials, is the fact that your variable, your predictor, is the month. And the month has a property that is not good for polynomials, which is the periodicity. So you expect that at 12, in some way, you match what you have at 1. But this doesn't happen with polynomials, even if, of course, you can fit a polynomial to pass through 2 points. But the thing is that the polynomial is working to fit all the points. So you must get a balance of those things. So maybe you could think of using this periodicity to get a better fitting. And so what you want is a periodical kind of fitting. So this is the third fitting I'm trying here, and this is the last one we do in that session. And so I want to use sine and cosine functions over time. So what I do is I'm using I will call this Cm, which is like a function which is the cosine of the month. So it's cos of month. But this is the idea. And what happens is that this should have the right periodicity. And with month, the periodicity is 12. But with the cosine function, the periodicity is 2 pi. So what I do is I multiply by 2 pi. Remember that pi is the number, 3.14 and so on. And then I divide by 12. So here I have the right periodicity. Control C. And here I define the same for the sine. So now I have these vectors that I will use to do the fitting. So my last regression is let's copy this maybe, and now this will be 3, and in that case my fitting will be using Cm plus Sm. So that means that the fit is one constant plus one constant by the first vector plus another constant for the second vector. So you have still 3 coefficients. So in this sense, it's not more complex than the parabola fitting. Here I need a 3. So let's see if I can enter this. Okay. And now try the regression. Okay. And now the summary. And you have here the summary with the coefficients. And notice what happens now. The R square is 0.95, which is better than the 0.87 we had before. So there is a clear improvement in the model, because now we are closer really to 1. And to see the plot, maybe I don't kill this one, and now what I do is I get coefficients 3 and 3. Well, I really don't care about this, but Control R, so those are the coefficients, and then Tm I have, so I don't need this, and then I will to plot my line. Sorry, I need to release this. Control C. And here is line empty 3. Here then I will plot this line with color, let's say blue. And here I have the first coefficient. Oops, for the second, for the com 3, and then here I have the Cm. The second is the one for Cm, and the third is the one for Sm. So let's see if this works. Okay, some error here. Oh, sorry. I see. No, the error is that now I'm using the time given by the vector Tm, so I should use this. See the problem. Here I must rebuild the cosinus for the Tm vector. So instead, no month, but Tm. And here it's the same. The sine of the same thing. Control C, Control C. I think it's the problem. Okay, now we did something, and that's it. Here you can see that using the periodic function first, the fitting clearly is better because it can go up to those points, but then it can fold here. This is something that the parabola couldn't do, and this corresponds to the periodicity because here you have the same value than here. So this is one way to improve this fitting, and 0.95 is really a very good fit. So in general, you should use information that you have about the phenomenon you are analyzing. In that case, of course, if I had data without meaning, the idea of periodicity maybe I shouldn't consider, but since I know that month is something which is like periodical, then I get the idea that the fitting could be periodical. So this has more meaning than just going to a high degree polynomials. In general, if you add many parameters, of course, if you use more dimensions or other frequencies and such, then you get better, even better R-square values, but the question is that you get a very complex model, and also you have overfitting. You are just trying too hard with the data you have, but when you have new data, the model won't follow the new values. So that's the example. I think that one exercise that you could do is I haven't done this, I think. This is the last pair, which is we did temp and energy, we did month and energy, month and temp. So the thing that still we haven't done is month and energy. So the month vector and KWH. So see what happened. Since it was linear respect to temp, no, sorry, since month and temp are no, sorry, since energy and temp are linear, when you do month and energy, you might expect something maybe related to what you have here. But this is just an exercise to finish this thing. So you can try to do a regression with the other variables, do the plot, and so on. Once you have done the plot, remember that you can save the plot here, save as the format that you like. In general, for, I don't know, could be a PNG for having a image file. But for working with LaTeX, for example, I think that PostScript or something like this is better. So PDF or PostScript. So that's it. So with this we finish this example about regression where you have been using data frames, so this is important for what will follow, and of course we'll come back again to the regression when we have done work with other algorithms. But regression is also one of the typical algorithms you can use, so here you have the mechanics of it. So that's all for this video.